கிளாஸ்ல கூலும் ஃபோர்ஸை பற்றி பார்த்தோம். இப்போ கூலும் ஃபோர்ஸ் வந்து ஒரு சிஸ்டம் ஆஃப் சார்ஜஸ் வந்து கொடுத்துட்டாங்கன்னு வச்சுக்கோங்களேன், எப்படி கால்குலேட் பண்ணுறது அப்படின்றத இப்போ நம்ம பார்ப்போம். இந்த ஃபர்ஸ்ட் ப்ராப்ளம் அப்படின்னு பார்த்தீங்கன்னா, சப்போஸ் ஐ ஹாவ் எ பாயிண்ட் சார்ஜ், நம்மளுக்கு தெரியும். சப்போஸ் ஐ ஹாவ் எ பாயிண்ட் சார்ஜ், then I am going to calculate the force experienced by this test charge capital Q, which is at a distance R. So suppose I take this is R hat, then the force experienced by the test charge because of the presence of the source charge. This is a source charge, this is source charge, okay, and now this is a test charge, okay. Now what is the force? The force is equal to 1 over 4 pi epsilon naught q by r square r hat. இது போன கிளாஸ்லேயே பார்த்துட்டோம், போன லெக்சர்லேயே பார்த்துட்டோம். இப்போ நம்ம என்ன பண்ண போகிறோம் அப்படின்னு பார்த்தீங்கன்னா, சப்போஸ் ஐ ஹாவ் டூ சார்ஜ் Q. So both are like charges. So நம்ம என்ன பண்ண போறோம் அப்படின்னு பார்த்தீங்கன்னா, we are going to calculate the force at the center. That means I am going to keep a test charge at this point. So with respect to the test charge, both the charges, source charges, are symmetrically distributed. இந்த சார்ஜ் என்ன பார்த்தீங்கன்னா, both these two charges Q. So small q ன்றது என்னது? Small q is a source charge and capital Q அப்படின்றது test charge, okay. So இந்த இடத்துல பார்த்தீங்கன்னா, both the source charges are symmetrically distributed about this test charge capital Q. இப்போ what is the force at the center P? இது நாம calculate பண்ணணும். So let us take this as a positive x-axis, therefore maybe I will take x-axis because this is on the line, okay. So suppose I can keep this இது கூட நம்ம என்ன பண்ணிக்கலாம் அப்படின்னு பார்த்தீங்கன்னா, ஒரு reference axis center கூட எடுத்துக்கலாம். So maybe we can take this as a center, okay. Let us that is origin of the axis, and this quantity I can take it as R, or this quantity we can take it as R, or sometimes we can take this as a X, this also you can take it as a X, so that doesn't matter. So it's a just a letter, okay. Now this is a something distance, this origin to this point, maybe I will take this as B, and this I am going to take it as a A. Now the distance between OB and the distance between OA are they are same, okay. You can take that one as an R, or if you don't like, you can keep it as X. Now what is the force at the center? So let me calculate this. The force experienced by the test charge because of the presence of the charge at B is Q, and this is due to charge at B, okay. This is equal to 1 over 4 pi epsilon 0 Q by R square, okay. And the unit vector along this direction, which I am going to call, and this is pointing in this direction. So source charge from Q to this Q, right? So therefore I am going to call the unit vector to be minus I hat direction, because this direction I will take positive I hat. So since this force is towards center, therefore I will put minus I hat. Similarly, F Q, that is the force experienced by the test charge at P due to presence of the small source charge, that is small q, at A. Okay, so this is equal to the Coulomb force is 1 by 4 pi epsilon 0 q by r square, but now the unit vector is along this direction, so therefore I'm going to put this I. Now what is the net force at the center? The net force at the center, that is the force on this capital Q, okay, which is nothing but the superposition of these two forces, that is FQQ at A plus FQQ at B. So now this you can substitute, and you can notice that these two forces, the magnitude part, that is 1 over 4 pi epsilon 0 QQ by r square, are same in both the forces. So let me take the common terms, QQ by 4 pi epsilon 0 r square, whereas for this part B and A, for A I will put I hat, for B I will put minus I hat, and these two gets cancelled. So therefore the net force at the center is equal to null vector, and this happens because these two are like charges, and we are calculating the force at the center, and there is a symmetrical distribution of charge. So the distance from this source charge and the test charge, and the source charge and the test charge are same. There is a symmetrical distribution of source charges, therefore the force at the center is 0. So let us try to extend this idea to the next level, that is suppose I have 3 charge distribution. So the 3 charge distribution is something like in an equilateral triangle, okay. Let us take this kind of thing. So there is a charge at this point, source charge, and source charge, and let us call this to be A, this point B, this vertex to be C, okay, this vertex is C, and therefore maybe let us put like this, okay. Now at the centroid of this triangle, okay, let me draw 3 lines, all of them are same distance, okay. So let us call this to be R. Now let us give a test charge at this point. So now what is the force at this test charge? Capital Q. So this is what we are going to calculate, okay. Now there are 3 charges, they are symmetrically distributed about the center, okay. So the symmetrically distributed, the term is very, very important, and therefore let us calculate this. So how to do that calculation? So in order to do this calculation, let me mark the axis for convenient. So let us take this as an x-axis, and this is y-axis, okay. The unit vector along this is taken I here, and unit vector along this direction is taken j here. Therefore when I express the unit vector along this negative x-axis, it should be minus I, and also for the downstairs, therefore this is minus j. So these are the unit vectors, okay. So let us now calculate the force at the center. And one more thing is, this total angle is 60 degree and this angle is 30 degree, okay. Therefore this angle is also 30 degree. The same way this also 30 degree and this also 30 degree, okay. So maybe used later, so just I'm telling. Now let us calculate the force at the center. Let us consider the first one, C, okay, the charge at C, the source charge at C, and because of this I am going to calculate the force at the center, okay. Charge, that is a test charge Q, capital Q. Now what is the force? F Q at C, which is equal to 1 over 4 pi epsilon 0 QQ by R square minus J hat. This is equal to minus QQ by 4 pi epsilon 0 R square J hat. Okay, so this we have calculated the force between force at C and the charge at C and the center charge, that is the centroid, and the charge kept at the center, that is the test charge. Okay, now let us calculate the force between the charge at A and the center, that is the test charge capital Q. So now how to do that calculation? So let me redraw here. Okay, so this is at the center, this is at charge capital Q. Now the force from the charge at A is something like pointing like this, right? So this is charge at A, okay, so this point, and it is pointing like this towards this center, that is test charge. So we can translate this force along this direction. Since this angle is 30 degree, so it should be 30 degree here. In the same manner, I can also write down the force at B, okay, the charge at B, right? So this is something like this, and the charge at B, that is capital Q, that is small q, the force due to the charge at B on the charge capital Q, that is center, so that can also be expressed, just a moment. So this can be expressed like this. Okay, now this angle is also 30 degree. Now because this angle is also 30 degree, now we can use the triangle of vector addition. Now this vector, maybe I will use the different color. Okay, so this vector, green color, and this vector gives the blue color vector. Okay, and similarly this green color vector and this green color vector gives the red color vector. So that is triangle of vector addition I am doing. Okay, now how to add these two? The first one, so the red one is because of the charge, the source charge at A, right? So let me write down the calculation, express in mathematically F QQ at A, which is nothing but 1 over 4 pi epsilon 0 QQ by R square. And now the point is very important, because I have expressed this x component and y component. This is x component, F maybe I'll put XA, and F y component because of the charge at A. Okay, so let me first write down like this. So F XA, this is x component, right, times I hat, because this is along positive I direction and this is along positive y direction. So F YA, and this is J hat. Now what is F XA? The angle is 30 degree, okay, and therefore this should be resolved. This vector, this vector, that vector which I am just drawn, is resolved along x and y. So therefore it should be the magnitude of this F vector, right? What is that? So 1 over 4 pi epsilon 0 QQ by R square cos 30 degree, because the adjacent angle is cos, therefore the angle is 30, cos 30 degree times I hat. The same manner, the magnitude of this will be 1 over 4 pi epsilon 0 QQ by R square sin 30 times J hat. So what is cos 30? Root 3 by 2. What is sin 30? 1 by 2. So let me substitute those things. So common terms are taken out, QQ by 4 pi epsilon 0 R square. So therefore this is root 3 by 2 I hat plus 1 by 2 j hat. Similarly, let me calculate the FQQ at B. So let me write down that. So FQQ B at charge at B, source charge at B. So the same manner, but this direction is here, right? The x component is minus I direction, therefore F, so let me write down here, this is F xb and this is F yb. Now what is fxb? Fxb times minus I hat plus fyb times j hat. Magnitude wise, when I write, this is 1 over 4 pi epsilon 0 qq by r square, and this component is a cos component, adjacent component, right? So therefore cos 30 degree minus I hat plus 1 over 4 pi epsilon 0 qq by r square sin 30 degree j hat. So common term when I take outside, qq by 4 pi epsilon 0 and cos 30 is minus root 3 by 2 here. This minus because I put minus sign here. So therefore cos 30 root 3 by 2 I plus 1 by 2 j hat. So now we can calculate the net force at the center. Okay, the sum of three forces F QQ at A plus F QQ at B plus F QQ at C. Now we can substitute three charges, the three forces which we have calculated. So in all the three cases, the magnitude is QQ by 4 pi epsilon 0 and there will be an r square here, right? So there will be one r square. So I will take r square outside. For A, I will get I get root 3 by 2 I plus 1 by 2 j. So let me substitute here, plus 1 by 2 j, plus for B, and I will get it. I will get minus root 3 by 2 I plus 1 by 2 j. For C, it is simply minus j. So I will put minus j here. Okay, so you can notice that the x component will vanish. Why it is vanishing? Because see here the x component is pointing along this direction and here it is pointing along opposite direction. So magnitude wise same, but they are points in the opposite direction, therefore it cancels out. Now you can also notice that if you add these vectors, qq by 4 pi epsilon 0 r square, and this half of j hat plus half of j hat is simply j hat with a minus j hat, therefore it should be null vector. Therefore the answer for this is null vector. Okay, the net force at the center is 0. So this is a very important observation, because now in the previous problem we have two even number of charges. There are two like charges and two like charges. They are symmetrically distributed. Now we have calculated the force at the center. And similarly, here there are three charges, that is odd number of charges. They are symmetrically distributed about this. The test charge is kept at the center, right? Now we can also extend this idea to four charges. Okay, so suppose I have a square. So let us take a square. Okay, so square. Now let us keep let us take A, B, C, D. We can also keep the charge at each vertex Q. Okay, now let us take the centroid. Therefore let us keep the test charge at the centroid. Now the distance is, let us take equal distance r, and this is also r, and this is also r. Okay, now we can calculate the force at the center. So before calculation, let me draw the axis. Let me draw the axis. This is x-axis, this is y-axis. Okay, if this angle is 45 degree, and therefore this angle is also 45 degree. So I can equivalently draw this diagram like this, like the previous case. Okay, so the force, so I'm keeping the test charge at the center. Okay, so the force, maybe the point, this point I'm going to call P. Okay, the center point I'm going to call P. The force at the charge at A that is experienced by the test charge Q will be pointing in like this, AP, right? So when I translate this vector, I will get something like this. This is that AP point. Okay, the force. So F AP. Similarly, let us take the charge at B, the source charge at B, and the force experienced by the test charge Q due to the presence of charge at B will be along this direction. I can translate this vector like this, right? I can write this vector like this. So therefore this force is F BP. Right? Similarly for C, this will be something like this. Okay, and this is F CP, and also the last one for D, I can write like this, right? F DP, and we know that every vector, so the angle is 45 degree we noticed, and therefore this is also 45, this is also 45, this is also 45, right? So let me calculate the force FAP. Let me express this. So magnitude wise they are same, 4 pi QQ by 4 pi epsilon 0, and there will be r square here because all the distance are same, because they are symmetrically distributed, and therefore cos 45 degree, right, times I hat plus sine 45 degree times j hat. So both are positive, it is in the positive quadrant. So this is x axis and this is y axis, so both are positive quadrant, so I will get like this. Similarly FBP will be equal to QQ by 4 pi epsilon 0 r square minus cos 45 degree I hat plus sine 45 degree j hat. Similarly FCP is equal to QQ by 4 pi epsilon 0 minus cos 45 degree I hat minus sine 45 degree j hat. So this is because second quadrant BP, second quadrant the sign is positive, cos is negative, that is why I am getting this. The CP in the third quadrant both are negative, and DP, and we have cos positive, sin negative, therefore fourth quadrant, therefore 1 by 4 pi epsilon 0 r square, and therefore cos 45 degree I minus sine 45 degree j, right? Notice that when I add all these vectors, you will get the net force, right? The net force, if we add, so magnitude wise these quantities are same, I can take outside. So cos 45 I minus cos 45 I minus cos 45 I plus cos 45 I. So I component, coefficient of I, they will vanish. So this is vanishing. Similarly sine, this is also 0, these are also 0, so the net force is 0. So this is another important thing. Okay, whether we have even number of charges or odd number of charges doesn't matter. Because of the symmetrical distribution of like charges, the force at the center, here it is centroid, and the net force is 0 always. Okay, So this is a very important observation, and one can also see another important point here. Suppose I remove any charge like here, for example in the triangle. Okay, suppose I remove the charge here. Suppose the charge at C I remove. Okay, now what will happen? Will it become zero? No. Even though this FAQ and the charge at A and charge at B, if you try to expand, you can resolve in a horizontal component, a vertical component. When we add, the X component vanishes, right? Doesn't matter. Now what happened to the Y component? It doesn't vanish. If there is no C, then the charge at C, then this part will not appear. Therefore, this will never become zero. So this is another crucial point. In the same manner, any number of charges symmetrically distributed, when you take the force at the centroid, it is always zero. Therefore, n polygon, okay, regular polygon. So if all vertices, okay, if like charges are kept, okay, and symmetrically distributed, okay, that means what? The distance from the center is always same. The net force at the center, maybe you can keep some test charge Q at center or centroid of this charge distribution or this regular figure n polygon. Then the force, net force at the center, okay, at the center is always null vector. Suppose we remove any one among the charge, then the symmetry breaks down, then the force are unbalanced, and hence non-vanishing terms appear in the net force. This is a very crucial point, don't forget. So now we can extend this n polygon case. So n polygon case இருக்குல்ல. Suppose now let us take n to infinity. Therefore it is something like n polygon. When I take n to infinity, it is almost circle. Okay, இங்கே point charge distribution பதிலாக இப்போ என்னன்னா, it is actually a continuous charge distribution. இதை பற்றி நம்ம அடுத்தடுத்த வீடியோவில் பார்க்க போகிறோம். Now what is the force at the center? Suppose I keep a charge, test charge here. Now there is a continuous charge distribution. Okay, so that continuous charge distribution மூலமா the force at the center F net is equal to 0. Okay, so இதை பற்றி நம்ம வந்து அடுத்தடுத்த வீடியோவில் பார்க்க போகிறோம். Okay, now let us try to solve a problem from Griffiths, Introduction to Electrodynamics. So this problem from Griffiths, so problem number 2.1, it's an exercise problem. A 12 equal charges Q are situated at the corner of a regular 12-sided polygon, for instance one on each numeral of a clock face. What is the net force on a test charge Q at the center? இதுதான் ஃபர்ஸ்ட் கேள்வி. இந்த கேள்வி பார்த்தீங்கன்னா 4 பார்ட்டாக பிரிச்சிருக்கேன். சப்போஸ் ஃபர்ஸ்ட் கேள்விக்கு ஆன்சர் பார்ப்போம். ஸோ லெட் அஸ் டூ திஸ் சொல்யூஷன். ஸோ ஒரு கிளாக் நம்மளுக்கு தெரியும், கிளாக்கில் வந்து பார்த்தீங்கன்னா 12 நியூமரல் இருக்கும். ஓகே, ஸோ லெட் அஸ் டேக் திஸ் இஸ் 12 and this is 6 and this is 1 and this is 7 and this is 5 and this is 11 and this is 2 and this is 8 and this is 3 and this is 9 and this is 4 and this is 10. Okay, so in the each numeral we will keep a charge Q, like charges Q. Okay, so this is the charge distribution. They are discrete charge distribution. They are symmetrically distributed. Yes or no? So this is symmetrically distributed. Now we are keeping a test charge at the center. So this is the test charge at the center. And what is the force, net force on a test charge Q at the center? Because of this reason which I mentioned in the previous, because of the reason which I mentioned in the previous case, so let us calculate the force at the center. Since we know that it's a symmetrical charge distribution and the distance are same, right, and if they are like charges, the force at the center, the net force at the center is 0. Okay, so this is the answer for the first one. So we have done this. So the answer for the first one is 0. So this is the answer. The second one is, suppose one of the 12 Qs removed, the one at 6 o'clock for instance. What is the force on Q? Explain your reasoning carefully. Suppose, see, notice that in the 12 charge distribution it's an even number. We already seen that either it's an even number or odd number. If they are symmetrically distributed about the test charge at the center, then the net force is 0, right? But suppose one of the charge, the second case, suppose one of the 12 Qs removed, maybe one at 6 o'clock. So suppose I remove like this, the one at the 6 o'clock. Now what will be the net force at the center? Notice that for each case, for example, one, the force experienced by test charge Q due to the presence of source charge 1 at 1 is balanced by the source charge at 7. Okay, in the same manner for 2 balanced by 8, for 3 the balanced by 9, and so on. The one charge at 12 is not balanced by the charge at 6 because there is no charge at the 6, right? So it is not balanced. The charge at 12 is not balanced by any charges. So therefore the net force is not equal to 0. It is actually, the net force is 1 over 4 pi epsilon 0 q by, maybe let us take the distance is r, so therefore r square and r hat. So let us take the distance to be r. Okay, so the distance to be r. So this is the answer for the second question. So the reason is this is not balanced. Okay, so that is why we are getting this. What about the third part? Now 13 equal charges Q are placed at the corners of a regular 13-sided polygon. What is the force on a test charge Q at the center? So like 12 charges, now we have 13 numerals. So this is the case 3. Okay, so maybe I will put 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, maybe 12, and this is 13. Let us take this 13. Now they are symmetrically distributed, therefore the force at the center is 0, right? Now let us take the last one. The question is, if one of the 13 Q is removed, what is the force on Q? Explain your reason. Same manner, suppose for example, see here all the charges are Q, right? The previous case all the charges are Q, correct? So therefore the force net is 0 for this case. Third one done. Now what about the fourth case? If any one of the charges is removed, for instance, maybe let us take the same charge at 6. So therefore the net charge is not balanced. So therefore you will get 1 over 4 pi epsilon 0 q by r square r hat. So I already mentioned that whether we have even number distribution or odd number distribution doesn't matter. Like 2 charge or 3 like a triangle or 4, and for a n polygon, it doesn't matter whether we have even number of charge symmetrically distributed or odd number of charges symmetrically distributed. Okay, so for all those cases at the center it is 0. Suppose I remove any one of the charge, then it is not 0, because then the net force is not balanced. So that is this is the answer for the last one. So thanks for watching this video. Okay, thank you so much.